We now want to look at how we can calculate bond angle and deviation from the normal tetrahedral value of 109 degrees 28 minutes or 109.5 degrees value for unstrained CH2 group. Take note, normal alkanes, for example for methane, the bond angle there is 109.5 degrees. If you want to express it in minutes, it's going to be 109 degrees 28 minutes. That is the bond angle for normal alkane, for unstrained CH2 group. But you know that when converting normal alkanes to cycloalkanes, there is a deviation, there is a distortion of this molecule because they are converting them to a cyclocompound. According to Baeyers strain theory, to do this, there must be a change in the normal value of what? The bond angle for this unstrained CH2 group, for this normal alkane. So how can we now get this deviation from this normal tetrahedral value of unstrained CH2 group? So that's why we have these formulas on the board. They are written here, so you can just quickly go through that. Bond angle for a given cycloalkane now that has been obtained from, of course, a straight chain alkane is given as 180 minus 360 divided by n, where n there is the number of carbon atom. So quickly, for example, if you want to calculate the bond angle for cyclopropane, how many carbon atoms do we have in cyclopropane? 3. That's very good. So all you need to do is 180 minus 360 divided by 3. Then 360 over 3 is going to give us 120. 180 minus 120, we're going to arrive at what? 60 degrees as the bond angle for cyclopropane. You can do that for other cycloalkanes. Okay, now having said that, let us now look at the deviation from the normal tetrahedral angle of 109.5 degrees. Once you get this bond angle, how can you now determine the deviation from this value? So you have equation 2 giving us the formula that deviation is equal to 102 times, you open bracket, 109.5 degree minus alpha, where alpha is the bond angle for the cycloalkane you are dealing with. Now I want to talk about total strain. To obtain the total strain produced, we now need to rely on heat of combustion. Is that okay? And the formula is given by equation 3 here. Now total strain is equal to number of carbon atoms. That's what this n represents. We are going to multiply it by the difference between the observed heat of combustion per methylene group and the observed heat of combustion per methylene group for normal alkanes or unstrained CH2 group. And you know what? This second part, that is the observed heat of combustion per methylene group for normal alkanes or unstrained CH2 group, is obtained from the value of that of cyclohexane. It's a reference value, there about 157.4 kilocalorie per mole. Is that okay? That's the value for that. It's a standard. It's a standard. But then if you want to calculate the observed heat of combustion per methylene group for any given cycloalkane, it's going to be the molar heat of combustion of that cycloalkane divided by number of carbon atoms in a ring. Take for an instance once again, for cyclopropane, the molar heat of combustion is there about 498 or 99, thereabout. Is that okay? So if you want to get the observed heat of combustion per methylene group for cyclopropane, it's going to be that molar heat of combustion for cyclopropane. Please put this down. Divided by what? The number of carbon atoms in cyclopropane, which is 3. Although in the next video we're going to bring out that formula once again. So once you get that value, just subtract the reference value here, which I told you is obtained from that of cyclohexane. The value is there about 157, like I said, 0.4. Okay, now having said that, let us now look at ring strain alone. Remember that here is total strain. This term in brackets alone refers to the ring strain. Okay, the ring strain. So you can convert it now to total strain by multiplying by what? The number of carbon atoms in the ring. Okay, now take note of this. Chemical stability can be measured either using heat of formation, heat of combustion, dipole moment, or absorption spectrum. But the most convenient of them is the use of heat of combustion. In the next video, we are going to see how we can obtain the observed heat of combustion per methylene group for a given cycloalkane, and of course, pick questions to solve to see how we apply these formulas on the board. On the board here, we have this question we want to look at in this video. The molar heat of combustion of cyclopentane is 793.5 kilocalorie per mole, and that of cyclohexane is 944.4 kilocalorie per mole. It is required that we calculate the bond angle of cyclopentane, the deviation angle from normal tetrahedral value for cyclopentane, the ring strain of cyclopentane, and of course the total strain of cyclopentane. And from the question given to us, what the values we know are the molar heat of combustion of cyclopentane and cyclohexane. So look at them here. We know their values. From there, we can calculate the observed heat of combustion for each. But when we get there, where we need to use it, that is for the ring strain and the total strain. I'm going to explain that. Is that okay? Let's look at the bond angle and deviation angle first. So the first part of the question, the bond angle, you would recall that bond angle alpha is given as 180 minus 360 divided by number of carbon atoms, right? So we are calculating for cyclopentane, N is equal to 5, because the cyclopentane, it has 5 carbons. So it implies that the bond angle alpha will be 180 minus 360 divided by 5. Let's work in this and see what that is going to give to us. Is that okay? So 360 over 5 divided by 5 is giving us 72. So 180 minus 72, that is 108 degrees, 108 degrees. So this is the bond angle for cyclopentane. Let us now calculate the deviation angle, that is the deviation of this value from normal tetrahedral value of 109.5 degrees. Alright, now the deviation angle, you would recall again the formula is 1/2 of 109.5 degrees minus the bond angle. So if we substitute here, this is 1/2 of 109.5 minus the bond angle is 108. Let's work in this and see what the bond angle is going to be. So 109.5 minus 108. So it's giving me 1.5. So I'm going to divide this 1.5 by 2. Divided by 2, that's 0.75 degrees. This is the deviation from the normal tetrahedral value of 109.5 degrees. Of course, you can see how close cyclopentane, its bond angle is to the normal tetrahedral value. You can see that, right? Good. We now want to look at the ring strain of cyclopentane and then the total strain of cyclopentane. We're going to take a short break. When we come back, we'll calculate that. But recall, we need to apply their heat of what? Combustion. And don't forget, the observed heat of combustion is equal to molar heat of combustion divided by number of what? Number of carbon atoms. And once again, don't forget that we'll have a reference value for number of, that is the observed heat of combustion for a given cycloalkane with respect to unstrained CH2 group. I told you earlier it's 157.4. So we're going to get all those and then solve for the third and fourth part of this question on the board after the break. You are welcome from the short break. Now I want to calculate the ring strain of cyclopentane and then move on to calculate the total strain of cyclopentane. First, the ring strain. Ring strain. That is given us the difference between these two observed heat of combustion. So we're going to write this. The observed heat of combustion per methylene group minus observed heat of combustion per middling group of normal alkane or unstrained CH2 group. So this is the formula. This second part of the formula is supposed to be given in a question because it is taken as a reference point 157.4. But it wasn't given here. Rather, they gave us the molar heat of combustion for cyclohexane. So we can get it from that part. Is that okay? We can get that value from that molar heat of combustion. What would we do? So our ring strain is equal to, what's the formula for calculating the observed heat of combustion per middling group? It's equal to molar heat of combustion divided by what? Number of carbon atoms in the given cycloalkane. So in this case, for the cyclopentane, the observed heat of combustion per middling group will be the molar heat of combustion of cyclopentane divided by number of carbon atoms there, which will be 793.5. We're going to divide it by 5. Then minus observed heat of combustion per middling group of normal alkane. Alright, I've written alkanes 2 times. Of normal alkane or unstrained CH2 group. I told you it's referenced to what? That of cyclohexane. So we're going to obtain it from the value of molar heat of combustion for cyclohexane given, which is 944.4 divided by what? 6. So let's see what this is going to give us. 793. 793.5 divided by 5. So this is 158.7 minus 944.4. 944.4 divided by 6. Good. 157.4. So you can see that value I've been highlighting since. And this is how they obtained it, 157.4. This observed rate of combustion per middling group for cyclohexane is the same as the observed rate of combustion for normal alkane. Is that okay? And that's why it's used as a reference value. In most cases, in the given question, it will be given. Is that okay? That's this part, it will be given. But if it's not given and they give you molar heat of combustion, of course, you can work it out. So the ring strain now, ring strain for cyclopentane will now be, we are going to have 158.7 minus 157.4. So let's see what we'll get. That is 1.3. 1.3 kilocal. That's the value down. Let us get the total strain now and see what it's going to be. IV. Total strain. Total strain will be number of carbon atoms times ring strain. Is that okay? So that will be equal to, for cyclopentane, it's 5 carbon atoms times 1.3. And the value is going to give us 5 times 1.3. That is 6.5 kilocal per mole. So that is the value as expected for this question given to us. And of course, this is how we apply the bond angle formula, the deviation from normal tetrahedral values, and of course the total strain. This is how we solve the problem.